I want to talk about Eulerian hydrodynamics now. Yesterday I talked a bit about smooth particle hydrodynamics. So now I want to give you a little bit the basics of some of the aspects of discretization schemes that are in use for Eulerian methods. And this is mostly a beginner's tutorial basically. So I will make you aware of some of the basic issues and also show you one of the widely used algorithms that is used essentially to advance ideal gas dynamics on a Cartesian mesh, say. So I want to start with hyperbolic equations, particularly the advection equation. If you look at the mass conservation equation that appears in the Euler equations, you can think about maybe simplifying this a little bit. Let's assume that in such a type of equation, the velocity is a constant. If the velocity is a constant, and let's also simplify this to 1D, then we have a generic one-dimensional advection equation, about the simplest hyperbolic equation that you can write down. And this particular type of equation is very useful because it highlights some of the fundamental aspects that appear when you try to integrate such hyperbolic partial differential equations. Now, I changed notation here from the rho to the q. So this is the quantity that we want to transport, we want to advect. And the velocity, the constant velocity, is this u here in the x direction. Now, the solution to this equation is actually very simple to write down. Right? You can immediately write down an analytic solution for this. So if you know the initial state of the field q as a function of x and t, if you know it at some initial time 0, you can write it down at any later time. That's the solution to it. Proof is simply by plugging this into the partial differential equation. It fulfills the solution. It fulfills the initial conditions also, so this is the solution in this case. And what this does is it simply moves whatever q is, suppose it's this sort of function here, it will transfer this to the right with constant speed. So that is what's called advection, that you just move some things through space. Now let's see, here we can calculate an analytic solution, but suppose we would like to do this for some reason numerically. So that we, for example, have a spatial grid of some kind. For example, a regular space Cartesian grid. Here some x coordinates that are discrete, and at those coordinates we know the value of the field q at some initial time t0, so as indicated here by these blue symbols. And what we would like to do in a numerical simulation is that we'd like to produce a time series, this state, we would like to have this at some later time, tn plus 1, and then again at some still later time. And the time step is sort of the difference between these discrete times. So this is what we imagine in terms of this numerical simulation or numerical solution to this problem. This is our partial differential equation, and we can readily think about a discretization scheme for this. For example, we could consider centered difference approximations to these two partial differential forms here. This is the time derivative, this is the spatial derivative. So we can write down an approximation to the time derivative like this, and here a spatial approximation, and that's centered difference because the time discretization here is just that I take at a certain point x, I will now find a difference, the states at time tn plus 1 minus the state at time n, and divide by the time interval. So this will be the approximation for this time derivative here. And similarly, I now make an approximation to the spatial derivative, and I'm using here a centered difference. That is, I'm at my point, going to the left and the right point. I'll take the difference here of the state, and I divide by the delta x. That's the approximation for my spatial derivative. So far, so good. And then you have this equation, and you can readily now solve here for the new state qn plus 1 at discretized point I. This is this formula. So we have now derived an update formula for the advection equation. And at that point, you would think, oh, I'm done. You program this up, say, and then you get a surprise. You, for example, you start out with an initial conditions like this. You have a step function. This is this initial condition. And then you move that for some time, spatially, corresponding to displacement of, say, 30 or so in the x direction. And then what you numerically get is this sort of mess here. It's oscillating like crazy, your numerical solution. So what's going on here? And that's a generic phenomenon that naive discretization formula like this for these hyperbolic PDEs will be often spectacularly unstable like this. Now, let's assume, we can easily make this, however, stable. And for this, let's assume that we know the sign of this advection velocity. Let's say we move to the right here, okay, with the advection velocity is positive. And then we modify our finite discretization, finite difference approximation to the PDE in the following way. Now we write the time derivative as before. So this is done by differencing these 2 points. But for the spatial derivative, we use something that's called upwinding. We go to the side from where the wind blows, so to speak. Right? We are here at this point I, and we only use upstream information. Because sort of the downstream part, the rationale behind this sort of intuitively is that the downstream points here, they will not really affect anything here anymore. Right? They have nothing to do with that point. Because that is going to be advected downstream, so I should not be affected by this. So any information I use here is probably spurious for this point. And with this upwind bias, you then have a new update formula, like so. And then, indeed, if you apply this to this problem, the advection of the step function, you get this. After a while, the step function is now nicely, perfectly stable, but there's one other important thing here showing up. Namely, the step function appears to be smooth. And that is called numerical diffusion. Okay, we see that this advection causes the feature to be washed out slightly. It's washed out, it's diffused out. And why is this called the numerical diffusion? I mean, obviously it seems to be sort of like a diffusion process. And you can actually make this more explicit by taking again a look at our discretization formula. For example, what we had used here was the upwind difference formula like this. This was our upwind difference. And we can just express it also like this if we want, here on the right side. And these 3 terms, so I have here the upwind difference, and I can write it as the center difference plus something else, and this something else is actually a discretization of a diffusion term. You have here a second spatial derivative for those experts among you. This is a typical second order finite difference formula, which you have in the diffusion term. Indeed, this is a diffusion term with diffusion constant proportional to delta x times the velocity over half. So that means the diffusion will be stronger if you have poorer resolution. Okay, and so that explains that indeed it explains why you see numerical diffusion. And we also see a lesson here. Once we add a bit of diffusion to the center difference, we add a bit of diffusion to it, and then it's stable. And that is also something that pops up all over the place in Eulerian hydrodynamics, that you have to have enough dissipation or diffusion or whatever to make these discretization schemes stable. Often without it, they can become very unstable. So adding this bit of diffusion makes it stable. Okay? And we also see that this diffusion vanishes in the limit of very small grid spacing. If you make delta x smaller and smaller, you can reduce that effect. That's also desirable, right? If you go to higher resolution, you then maintain the sharpness better, you have less diffusion then. So, but now let's return to the Euler equations, which is really what we are mostly interested in. And those are so-called hyperbolic set of conservation laws. And we can write them formally in a useful way. If we define, for example, a state vector, which can be the state at a point in space of the fluid, which is characterized by the density of mass, rho, density of momentum, rho times v, and density of energy, rho times e. And the energy here is composed of a thermal energy per unit mass and a kinetic energy per unit mass. Then, if you have this sort of formal vector, you can write the whole set of Euler equations quite neatly in this form. The time derivative of this state is just the negative divergence of a flux. And this flux vector encodes now the real physics of the equation that tells us how mass, momentum, and energy is moved around. So this encodes this whole flux vector, how this is called, which is a function of the state of the fluid. That encodes how the Euler equations transport these quantities. But now you see explicitly that there is a conservation law here, just like the continuity equation itself, for the integral of this state, which is then the mass, momentum, and energy. Right? On this form, this is very explicit. You also need the equation of state. Now, what is very often used in practice is a so-called finite volume discretization. You now take this differential law and you tessellate space with, for example, a Cartesian grid with cubical cells. And what you then want to have is the average state represented in your simulation on this grid, the average state in a cell. How do you get the average state in a cell? Well, you average over the state, right? So integrate this mass, energy, momentum density over a cell, and then you get what is contained in a cell, namely the mass, the momentum, and the energy. And so you integrate this over the finite volume, and you might want to call this, say, a state vector of conserved quantities in a cell, which is then the mass, the momentum, and the energy. And then you see that if you add this all up over all cells, you will have just the total mass of the system, the total momentum, total energy, and these quantities will be conserved. That's the nature of this hyperbolic system, that we are conservative. And also, if you now integrate over the volume, this whole equation over the volume, you can see that you can exchange the time derivative. And if you integrate u, then you have the state q. This gives you a time derivative of the state, the conserved quantities in a cell. And the integral of space over this divergence you can cast with the divergence theorem in a surface integral. So what you then know is that the time evolution of mass, energy, and momentum in a cell is just given by the surface integral of so-called fluxes in and out into a cell. Intuitively, it's very clear what's going on. So we just balance whatever, say the rate of change of the mass in a cell will be equal to the mass flux into the cell. That's all what this expresses. And we would like to, on this basis, would like to now construct numerical schemes that are explicitly conservative, that calculate directly these sort of mutual exchanges of conserved quantities between adjacent cells. Now, the whole issue now is how to compute the fluxes themselves. Basically, this is the central task in Eulerian hydrodynamics, to calculate the fluxes, such that an accurate and stable, robust scheme results. That's basically everything is ultimately boiling down to this, because implementing this sort of equation, once you have the fluxes for a cubical cell, is very easy. Now, many of these schemes, and there are really a bazillions of different flavors of Eulerian hydrodynamical updating schemes, many of these schemes can be described loosely as variations of so-called reconstruct, evolve, average steps. And that means that an REE scheme more or less proceeds through three steps that I would like now to explain. It basically, a time step has always a reconstruct step, basically an evolve step, and an averaging step. Sometimes they're not very explicit, but basically conceptually they're often doing exactly this. So reconstructing means that if you know in a discretized system the state at a sequence of coordinates, say these are the xi's, here we know the state of the system, these u's, then you would like to extend this knowledge that you have at sort of as an average over the cell to some continuous description of the state of the fluid everywhere at every space coordinate. That's called spatial, or that's called reconstruction. And the simplest possible reconstruction is simply a piecewise constant reconstruction. That means, well, you actually assume that the state is everywhere constant in a cell, right? So that the density, for example, in the cell is constant everywhere. Then the density field would be a piecewise constant function like this. This is the simplest thing. You will later see that you can also be more fancy, and if you need to be more fancy to get better accuracy, actually. Then, once we have this reconstructed state, then we want to evolve it forward in time over time step delta t. And particularly important is the so-called Godunov's approach, where this is done by treating each cell interface as a piecewise constant initial value problem, which is solved with a Riemann solver. So we'll discuss this later, what this precisely means, but what it means, we take this really as a physical initial value problem, and now we try to construct an analytic solution how, for example, this piecewise constant state around this particular interface evolves over delta t. And in fact, this is, in each case, then a so-called Riemann problem, which you can solve analytically for the ideal gas. Or, for more complicated situations, sometimes you need to solve it approximately. But we want to more or less solve, in the evolve step, each of these little problems and see the waves that propagate to left and right more or less exactly. Once you have the solution at the end of the step delta t, what you then do is you say, I'm averaging this again. I'm basically redoing what I've done in my finite volume discretization. I'm now saying the evolved state, which has substructure in the cells, is now thrown away again. I'm averaging over this evolved state to calculate a new average state in a cell, right? Then I start the whole cycle again. That's basically what many of the Eulerian codes do. So clearly the crucial step is in the middle here, the evolve step, and that is basically, as I said, a Riemann problem approach. That's what Godunov suggested, and it's a very powerful, widely employed approach. So here you view as a Riemann problem the initial value problem that you have at every phase interface between two cells. At every interface between two cells in your grid, you will have then a left state and a right state like this. What you now would like to do is to calculate how these states evolve. So as I said, you assume piecewise constant left and right states for the fluid, and the fluid is characterized, for example, by the three primitive variables, the density, the pressure, and the velocity. And we make this all one-dimensional, so the velocity is here in the direction of x here. Okay. So this is called a Riemann problem, basically. This initial value problem for the ideal gas, piecewise constant. This is the Riemann problem. We looked at Sot-shock tubes yesterday. That's a subclass of these problems where the initial velocities are 0. But generally, they don't have to be 0. They can be anything. So you'd like to calculate the general solution to the Riemann problem. And the general solution has this structure. Turns out that by analyzing the characteristics of the Euler equation, you can show that the general solution structure of this sort of Riemann problem will have consists of a set of waves that emanate from the origin. And in fact, there's always a so-called contact discontinuity in the middle. This is one wave. And this contact discontinuity is sandwiched by either two shock waves on the left and the right side, or a rarefaction wave and a shock wave, or two rarefaction waves. All these three possibilities are possible. But you always have this general wave structure. Contact discontinuity sandwiched by either shocks or rarefactions. And a shock, we discussed what this is. So a shock will, and these three nonlinear waves, they propagate with constant speed into the media. These are indicated by these lines there. Okay, so and this is actually self-similar issue. Once you calculate these waves and their wave speeds, then you know the solution to arbitrary times. Because here we assume that the right and left state extend to infinity. That's of course not true, right? Also tells you already that whatever we're doing, we can only apply is that delta t must be small enough such that these waves start to go out in those directions. Maybe they should not interact with the waves that come from the next cell interface, because then your analytic solution will break down. Once these waves interact. So that is a time step constraint. Basically, you need to make sure that your time step is short enough that these waves don't intersect in the middle. That is then the so-called Courant time step criterion. So now, what basically, here's an example how this looks like in a SOT shock tube. If you have, for example, as left state the density is 1, and here it was 0.2, then after a while you might get as a Riemann solution something like this. That, and here you see the wave structure. Okay, the rarefaction wave is bounded by this point and this point, and that's where the gas is simply expanding. Here the contact discontinue is this jump here. This is the blue wave, and then on the right there's the shock. So that is basically the Riemann problem. You can solve that wave structure for every combination of initial densities, pressures, and velocities. And then Godunov's flux now says, oh, what we really need to take, all that's interesting to us here is actually we want to know what is the state of the fluid right on the interface, because that will give us the flux. So Godunov says, now let me read off here what is the state of the density, pressure, and the velocity. So that would be based this point. That's all I need from the Riemann problem. I want to know the flux at the interface. I don't actually have to know all the wave structure necessarily. Okay, I just need to read off where am I in this wave fan, right? And that is a nonlinear answer to this initial value problem. What is the structure directly at the interface? And then finally, once we have now the Godunov flux, question is how do we now average this? How on earth? That seems like contradicting what I just said. Averaging would mean that I, for example, would have to, on the right side, suppose I want to average state of the cell that's lying here on the right, then I would have to take this solution and calculate from it the average density. Okay, I mean, this seems to be doable. Okay, I need to integrate here the density field or here, but for example, on the left side, I have this inclined, which is not exactly straight either, this rarefaction wave. I need to integrate somehow the density underneath it to get the mean density of this state. That seems to be quite elaborate. Fortunately, however, you actually don't have to do this explicitly. You see this like this. If you take the Euler equation again, this is here on the right. The Euler equation is a 0, right? We have the time derivative of the state plus the flux in one direction. Now let's integrate this in time and in space. I can integrate this, and if you expand this integration, you get this, that you, for example, do the spatial integration here at the final time and at time tn here over the state. This is this first integral where you can undo with this time integral the partial derivative in time. And on the other part, on the f, you can basically undo the spatial integration here, and then you're left with a time integration. Okay. Now, if you look at these four terms, you see that this here is actually, since this is the state, the new state at the end, Tn plus 1, and want to put in the average state here, this whole integral, if this devolved solution, this will be equal to the average state times delta x, because actually that's just the definition of the average state. The average state that I want at the end would just be the integral over the evolved state, which is this, divided by delta x, right? So I can replace this with the desired average state times delta x. And this here is what I start out with. This is the average state I start out with times delta x. More problematic seem to be these things, because they say I need to integrate the flux over the time interval of my time step. Oh, seems to be hard, but now remember what I just said, that the solution of the Riemann problem is actually self-similar in time. So the flux is time independent, okay? The flux actually at every interface is time independent and is given by the Riemann flux. That means the averaging is trivially done, and I can just write down the update like this. The new state, the new spatially averaged state is the old spatially averaged state times delta t or delta x. The flux difference, whatever comes in from the left side minus the things that go out on the right side of the cell. That is how we update things. But now, once we have understood this, so we basically have now all the steps of the reconstruct evolve average procedure in Godunov's approach, but there are two issues left open. This is, I should say, what we've just done was with spatially constant, piecewise constant reconstruction. This is a so-called first-order accurate scheme. This is the first-order Godunov scheme, what we just discussed. But there are two issues open. One is, how can this be extended to multiple dimensions? I just discussed 1D at the moment. And then also, how can we extend this to higher accuracy than first order in space and time? So let's first look at the extension to multi-D. So this is the Euler equation in full glory. Now we can write this out into components, and then you get such a ugly looking thingy. This is the component form of the Euler equation in Cartesian space. Here the velocity is, as it's often done in the field, is written as UVW for the x, y, and z components of velocity. And then the Euler equations look like this. Okay, pretty nasty. But then you can sort of try to compactify this a bit with better notation, and you can, for example, write it like this: that this is the partial time derivative here is of the state u, and then you define with f just the flux in the x direction, which is this first vector here, and the g is the flux in the y direction, the h is the flux in the z direction, and then you have this partial derivatives x, y, and z in each of these directions. So that is another form of the Euler equations. And the h, as I said, is this vector, g this and this, right? And now you make the trick of so-called operator splitting. I'm boldly conjecturing now that I replace this one equation with three equations, like so. Each of them looks like a one-dimensional Euler equation, dtu plus dxf, and then I have same thing in the y direction and same thing in the z direction. Now, the question is, is this really the one-dimensional Euler equation? Not quite. It's a so-called augmented 1D problem, right? This is effectively the only degree that's, spatially the only difference here is in x, yes. But the f vector has still some variables related to the y and z direction, and they're kind of passively going along for a ride in this equation. But they're still there. This is an augmented 1D problem here. And this in the x direction, this is an augmented 1D problem effectively in the y direction, and so on. But because this augmentation, these additional variables, they cause nothing, no problem. I can just treat them along with passively, basically, in my Riemann problem. They are just sampled at the right location. And so I can basically, with the technique that I previously discussed, solve this problem, say with an operator x delta t that gives me the update in the x advection over delta t. And similarly, I define, say, an operator that does the solution of this part and an operator that does the solution in the z direction. And now I conjecture that I can actually approximate the solution at time tn plus 1 by applying these individual operators one after the other. And actually, for the linear advection problem, this would be exact, okay? Because it doesn't matter, basically, if you are you can, if you want to go diagonally, you can also go first on the x and then the y, and you end up at the same place at the end. So for the linear advection problem, this sort of decomposition would be exact. For the Euler equation, it's not exact. It's some sort of approximation that is, however, reasonably low order accurate in this case. But to get second order time integration accuracy, I need in this operator splitting approach actually do something more. I need to suitably alternate the application of these operators. For example, in a two-dimensional solution scheme, these are called sweeps. I could first do a sweep in the x direction to update the x dynamics and then the y dynamics. But that would be very unsymmetric. I would always do the x first. And so it's actually better to, for example, consider something like this. It would apply an average of doing it first with x then y, and alternatively doing it first with y and then x. So you'd alternate this, but you could also alternate this differently. For example, like this, that you would do first, similar to our kick, drift, kick, leapfrog idea, that we would do a first and a half x sweep, then a full y, then a half x. And there are many possibilities to do this in an operator split approach. This generalizes also to 3 dimensions. So often what's done is that one alternates the sequence of how these operators are applied. For example, you would first do an x, y, z, then again a c, then a y, and an x. Okay, and then you have also second order accuracy in time. So this is one possibility to do a so-called operator splitting approach. You can also come up with unsplit schemes where you calculate the fluxes simultaneously, basically in the x direction and the y direction, and then you would update the states in one go, like this. This is called an unsplit scheme. Such unsplit schemes are also possible, for example, for unstructured meshes. Here you would use the general formula that comes from the divergence theorem, that you integrate the fluxes over the surface, and then you have to somehow estimate the fluxes over the whole outer boundary of such an unstructured cell. You're not necessarily required to have a cubical cell. Could have triangles or hectagons or whatever, and then you would have to usually use an unsplit approach. So the other important aspect is how to achieve higher order accuracy. So we saw before that the basic first order accurate Godunov scheme would use piecewise linear reconstruction like this. And I think it's clear what probably is the next step to that. To do a better reconstruction, you would like to do, for example, a piecewise linear reconstruction. And the piecewise linear reconstruction that might look like this, the red line now here, this would be basically the run of, for example, the density field through this field that you guess. Okay, you take basically as input this, and then you make a smoother version of that piecewise linearly. How do you do that? Well, you estimate locally a gradient, and then you replace the piecewise constant run of the density with a piecewise linear one. And you do it such that the integral under this approximation maintains the same mass that is in the cell. So you basically make a conservative reconstruction. Still has the integral under this red reconstruction must be the same as the integral under the gray area. But now, when you estimate the gradients, there is something subtle here. And it's kind of indicated with these dotted lines. Okay? So these dotted lines are so-called, these are basically the actual gradients that you would estimate. For example, here with this steep dotted line, you would normally be here in the middle, and you would take this left value and the right value, and you would think there is a steep gradient towards the upper left. If you would actually use this very steep gradient, you would predict the occurrence here that there would be a little hole developing here, because you would predict the state on the right side of this cell to be pretty low, actually lower than this guy as your neighboring side. And that means if you would just use this slope here that you estimate, you would introduce a new extremum here. You would introduce here a minimum, a little hole, and such minima or new extrema, they create numerical oscillations in the solutions that are unphysical. That's why one needs to apply a so-called slope limiting procedure of some kind. So what this means is that one estimates slopes, gradients of this field phi somehow with an ordinary second finite difference approach. Then you need to multiply this with some nonlinear switch that usually is 1. Normally you would like to maintain this estimate of the slope, but sometimes when a situation like this is detected, you would like to make this gradient shallower, so then this alpha will go down close to 0, or maybe even all the way to 0. This is called the slope limiting. And this is needed to prevent the creation of new extrema, which then creates spurious oscillations. And it will also reduce the order of the scheme, because we're then going from a piecewise linear again to a flat piecewise constant reconstruction, which is first order accurate. This will see a second order accurate. So once you apply strong slope limiting, you reduce the order of the scheme. And turns out this is necessary at discontinuities usually, like here. You then need to become more diffusive there, need to be lower order. And the slope limiters themselves, there's a whole slew of possibilities how this is done. This is a simple variant of a so-called min-mod slope limiter. But if you open books on PDE solvers, you'll see that there's a whole slew of possibilities how to do this. And then there are, people are of different opinion what's best in certain applications. Now suppose we have these slope-limited gradients. What we then need to do to go to higher order is to, before we apply our Riemann problems, we need to go to the left and right side of a phase. And here we now use the slopes to interpolate the state of the fluid from the center to the edge of a cell. That's done with your gradient, like this. For example, if you are in this interface I plus a half, so here is I, and I would like to have the left state of the interface I plus a half, which is this interface. The left state comes from the cell I, so I go to row I, and I need to take the gradient of I and interpolate this with half a cell size to the right. Similarly, for the right state of this interface, I need to go to the cell on the right, which is the row I plus 1 cell, and there I need to go backwards to the left, so I have a minus sign here with the gradient, and interpolate this with delta x half. Now, this unfortunately is not the whole story. To get second order accuracy, we not only need this in space, we also need this in time. So what you actually would like to do is to have the state in the middle of the time step. So what you do here is you also add in a half-step prediction forward in time. So what we actually need to do is also to apply a temporal extrapolation to the mid-step in time. So we want the state not at t0, but at t0 plus half the time step into the future. That would be something like this, right? That we need to add here the time derivative in cell I times delta t half. Similarly, on the right side, we need to add the time derivative times delta t half. And that is actually not only for, say, the density, we need to do this for all the variables we have, the density, the pressure, say, and the velocity. So this is what we want to have, which brings up the question, how do we get the time derivative here that we need? Because we don't know the future yet, right? So that's what we want to calculate. So how do we get the time derivative? We cannot get it by finite differencing. But there's a simple trick to get this. And that's done in the so-called Mussel-Hancock scheme, which is very popular for that reason, because that's doing this in a very simple way. We look at the Euler equation again. The Euler equation is minus the flux divergence, but we can also write this differently. We can first differentiate the flux with respect to the state, and then apply the spatial derivative only to the state. And that what's in the front here, this is actually Jacobian of the flux vector. This Jacobian we can readily calculate for the Euler equation. That's okay. So we can express the Euler equations also if we want like this, that there is this Jacobian there. Or in other words, we can use the Jacobian together with the spatial derivatives of the state to get the time derivative. And that's now the central idea. To get the time derivative, we take the Jacobian, just multiply it with the derivative of the state with respect to x, which we actually have, because that's our gradient estimate, right? So we can, with this formula, we can now use our gradient estimate and make out of it also an estimate for the time evolution. All we need is also the matrix, the Jacobian evaluated with the current state. So that is the neat idea, because it allows us now to do a half-step forward prediction and a spatial prediction all together in this sort of formula. All we need is the spatial gradients for this. And then we have these states are then fed into the Riemann problem to calculate the fluxes. Nothing else needs to be changed, and at that point you then have a second order accurate scheme. Right? All you have to add is basically a gradient estimation and a slope limiting procedure. As I said, at discontinuities, the slope limiter will suppress the derivative, making the scheme then automatically first order. This is, by the way, also interestingly related to sort of Godin's theorem. You intuitively know why this is probably required, because he has shown that any linear algorithm that does not produce new extrema is total variation diminishing, can be at most first order. So this scheme is what we have is not really exactly linear, but it's clearly intuitively related to this sort of behavior. Basically, this says, Godin's theorem, that a simple algorithm cannot be simultaneously first order and total variation diminishing. So maybe a few comments now in order. So what I've just shown you is sort of a complete algorithm to write a Eulerian code that is actually quite accurate, quite decent. And similar schemes are used by codes like, at least as far as second order accuracy is concerned, by codes like Athena or Ramses, also a repo. And then there are higher order extensions still, which I have no time to mention. Piecewise parabolic method, for example, is conceptually basically you're replacing the piecewise linear reconstruction with a piecewise parabolic reconstruction, and that allows you to go to higher order of accuracy. This is more subtle to make this extension, but basically this is the conceptual idea. So maybe some of you might now ask, so why is there no artificial viscosity needed in a muscle scheme? And how is actually entropy produced? I haven't talked about this at all. Indeed, you don't have to talk about this in this mesh codes, because that's kind of taken care more or less automatically. And to realize this, you first of all have to understand that the temperature, which is of course intimately related to the entropy, is here very indirectly defined, always as a difference between total energy and kinetic energy. This also means that this scheme will have accuracy problems if this difference is between two very large numbers. Or in other words, if the flow is kinetically dominated, very cold, then the temperature will not be very accurately determined anymore, because it's kind of unimportant what the temperature is, in a sense, because the pressure force will be small compared to the ramp pressure. And indeed, this is often then described as cold flow problem, that if you have this situation that kinetic energy is much larger than the thermal energy, and it's so dominating the total energy, then this subtraction of these numbers in the discretized regime will not be very accurate often. And the entropy we don't need to follow explicitly. Essentially, one simply assigns the entropy according to what the conservation laws dictate. And since we do follow them as well as we can, probably the entropy will behave reasonable. Basically, that's sort of the attitude. And indeed it does. I mean, normally it will only go up, but if your discretization scheme does something wacky, maybe it does go down in some cell. But in general, it will behave physically correctly. And sort of the breakdown of the differential form, the Euler equation is sort of here avoided, because we go to the integral form of the equations to describe how they exchange the fluxes. And that exploits the continuity of the fluxes. So finally, I mean, basically, I'm make just a few, one more comment, and let you go skiing then. That is about the Riemann solver. So here in the literature, you will find that there's a lot of discussion about different types of Riemann solvers, approximate Riemann solvers. This is also a technical area for the most part, because it's possible to solve the Riemann problem for the ideal gas exactly. Well, So you can use that. You can use a so-called exact Riemann solver, but that requires iteration. So you need to, there is a nonlinear root finding required, and you have to iterate to solution. It's not overly expensive, but a little bit. So sometimes you might want to get around this. And also for more complicated hydro problems, especially if you add magnetohydrodynamics, the Riemann problem becomes very complicated. And that's why the exact one, that's why you would like to come up with approximate solutions to the Riemann problem, which turn out to be equally good in practice often than an exact Riemann solver would be. And one example, I just want to give you one flavor of, for example, how this can be done in the case of the row solver. Let's look at how this is done. Here we consider, just for simplicity now, let's consider isothermal gas. The isothermal gas will have no, in 2 dimension, would have a state vector, just the density, then the momentum density in the x direction, momentum density in the y direction. And since it's isothermal, you don't have a thermal energy equation. Now, the x sweep part of this equation, you can do operator splitting here and define a flux in the x direction. For the isothermal flux would look like this. You see here basically the x coordinate of the momentum density, and then, and here you have the augmented problem in the y direction in the f flux. So that's the x sweep of, and what we would like to do as usual is have the update scheme like this, and what we need is the flux approximation. Again, you could do this with an exact Riemann solver, but now let's see how we would do this with a row Riemann solver. And the idea of row is, and it's similar in many other approximate Riemann solvers, is that we take the hyperbolic equation in this form. So again, we put in the Jacobian there, and then we linearize this. And the linearization is achieved by, we would like to make the Jacobian independent of space. So making it a constant and time. And for example, you would like to come up with an approximation to this Jacobian that depends only on the left and the right state of the interface. And there are certain consistency conditions for what such approximation should be. But let's assume that you can make this, and that's now where basically insight comes in. Rho, for example, suggested this sort of approximate linearized Jacobian that depends only on the left and the right state. So then you can, once you have linearized this problem, you can consider this matrix, the A twiddle, this linearized Jacobian, and consider the eigenstructure of this matrix. You find it has eigenvalues. The U tilde is some average velocity of the left and the right state. And then Cs is the sound speed, the speed of sound. So there are 3 eigenvalues of this advection equation. And one is, has an eigenvalue, a wave speed, that is just the current velocity basically of the gas, the average velocity, minus the sound speed. So there's something going to the left. And then there's something like a contact wave, a wave going to the right with the sound speed. And there's something that is sort of just moving with the constant, or with the average fluid velocity, which is sort of like a contact wave. And these, you can also calculate the eigenvectors for those eigenvalues, for example, like this. And you can do this algebraically. And for the row case, you can also do this algebraically for the Euler equation. And this is sort of the wave structure that I meant, that you now in general will always have then this wave that's going with the speed lambda 3, and then one wave to the left, just shifted by 1 times the sound speed, and one to the right by 1 times the sound speed. And then you can construct the linearized solution very easily. You expand your jump in between left and right state. You expand this in this basis. And then you have the solution in linear form of the linearized equation. And then you can basically write down for this approximate solution Rho's flux like this. And basically that's it. And then you can use that, and it works in practice very well. And similarly for the Euler equations. So I'm now at the end of this. Are there any questions? Okay, this means it was too easy, or you are shocked. Yeah.
So this part where you use so the Jacobian has spatial derivatives, and you said that you use that to estimate the time evolution.
Yeah.
That wasn't entirely clear to me.
Okay. Let me repeat this. I guess this was here. So here's the Euler equation. Okay, this part is just this is just look at the first equality, right? This is the Euler equation. Normally, one puts the flux to the other side. It's the conservative form, and all I now do is I apply basically chain rule here, right? I say, okay, this is equal to the derivative of f with respect to u, and then u with respect to x. Yeah? So this is the chain rule here. Right? Chain rule, and then you have here basically that you get with this that the spatial derivative of u, right? And that is just again the same thing as here on the right side, right? The chain rule puts in the Jacobian here. Yeah.
So what if we have two advection modes, and then they are evolving separately, and then do we need any modification at the overlap of two evolved advections?
Let's see whether I understood this. You're saying you have two advection modes?
Yes. So at two different position and time, maybe two different positions, they have two different advection
Velocities?
motion. Yeah.
Yeah, I mean, this is basically the general case, that the advection velocity is a function of space, right? So what I initially showed you is that if the advection velocity is constant throughout space, then the advection problem is particularly simple. But you're right, in general, the advection velocity will be a function of space. And then, as for example, in the Euler equation, that's the case. So the wave speed, for example, can be a function of space, and in general will be the case. And so then you have to apply this more complicated formalism, basically. Then determining the upwind side is not so simple. It could also change, right? Somewhere the wind blows in this direction, at another place blows in another direction, right? Yeah, so you have to apply these more complicated formula. Yeah.
Why are you allowed to split the Euler equation into 3 parts?
Whether I was allowed to?
Yeah.
I haven't asked for permission, yeah. But yeah, this is something, I mean, in the limit, you can show that this is sort of the operator splitting. This is not the same. So once you split it, you basically change the nature of the problem, okay? And here, this was this replacement by saying I can take the full Euler equation, I replace it with these 3 equations, and by subsequently applying them alternatingly, I have the same net effect as doing them sort of simultaneously. And that is sort of intuitively clear that at some level this should probably work, but it is a different problem and you make an error here. So replacing this with this is causing an error. And you then have to see whether the error that it makes is sufficiently small. And you can show under certain conditions that the error becomes smaller, the finer your grid size, the finer your time step becomes. But sometimes, for example, this will break, always this directional splitting will break often the exact isotropic nature of the Euler equations. For example, if you have whatever, suppose you have a point explosion, and if you first treat the explosion, let it explode a little bit in x direction, a little bit in y direction, and a little bit in z direction. Because the explosion, the little bit that you do in the y direction will already be affected by what you have done in the x direction. So it will not be always the same, will not necessarily stay perfectly symmetric because of that, right? Once you do that. But experience shows that this is usually okay, but not in all cases. With an unsplit scheme, you could avoid that. But you know, the reason why these directional split things are very popular is because you can basically recycle. Originally, the historical reason was that people were then able also to recycle just the 1D codes, right? You can then just say, I'm applying basically, you can have the same subroutine doing all the work both in the x, y, and z direction if you write this clever, right? I think we are over time, right? So if there are no
Okay,
further
if
questions.
there is no other question, I think we can really thank Volker for this excellent